Okay, so it is a long morning. So what I would like to tell you today is how we detect the prompt earthquake gravity signals, and different people have been involved, of course, in this work. People from the seismological community with Jean-Paul Ampuero and Pascal Bernard and Kevin Juel, but also some people from the gravitational wave community, because it is what I would like to tell you is that it's a collaborative work between different fields. And actually, that is the story. It is a narrative of, of this work. And I will like to show you how it was not evident to convince people that we had this signal. And actually, everything started about 10 years ago when people from Virgo contacted me because they have this big instrument. You know, it is this interferometer here installed in Pisa in Italy. It is a Michelson interferometer with two arms of 3 kilometers long. And the basic idea was to use this interferometer as a seismic gradiometer to use the different instruments installed on the arms to detect some components of the deformation tensor and eventually the rotation between the two arms. And I was, at that time, I didn't know anything about this kind of instrument, but I was very impressed because if you look at the system, they have some, what they call the marionette system, which is an inverted pendulum, which makes it possible to stabilize the whole system and the mirror, for example. And they were able, at high frequency, to go down to 10 minus 24 in sensitivity. It's quite impressive compared to what we are able to do in seismology, as I will show you later on. Okay, so the first motivation, well, that was the motivation. And the first work we started with was a theoretical work to work on synthetic seismograms of the effect on the gravity field by using the normal mode theory. Normal mode theory is a theory which calculates the free oscillation of the Earth, and it's a simple way to calculate the synthetic seismograms. And normal modes are also sensitive to gravity. So what we did, we started to calculate synthetic seismograms for the Tohoku earthquake, and we were very surprised because just at the beginning of the seismogram, there was a small signal, quite small, but completely unexpected. Of course, afterwards, we see P waves, we see surface waves, we see the classical seismograms. But this signal at Virgo was quite small. I give here the order of magnitude. You have to keep in mind what is a microgal, because in gravity community they speak in macrogal or nanogals. And when we do the calculation, it is a 0.3 nanometer per square second. So it is really, really very small signal. And we say, okay, it's a very small signal. Could we try to observe it in the Virgo interferometer? But actually, I will show you that it's very difficult. Okay, so this signal quite small and at 10,000 kilometers. So it means that it was almost an instantaneous signal. That's the reason why the gravity perturbation is propagating at the speed of light. It is the reason why we wanted to try to look for this tiny signal. And so since the beginning, we realized that it might have some important applications in earthquake early warning system. Okay, so what can we try to understand what's going on. And by the way, it's interesting to realize that the first free fall experiment was done by Galileo about 400 years ago. And of course, following this free fall experiment, there was a gravitational law of Isaac Newton some years later. And so what's going on? When we have an earthquake, we have two blocks, and they move together. So we have, for example, if you have this movement, we have a variation in density on this side and on both sides of the fault, and negative variation of density on the opposite side. So it's a quadrupole, which explains why the effect is so small. But you have also some other effects. You have also perturbation of the free surface, and which can also affect the signal recording very far. Okay, so basically we have this mass redistribution related to the this term, and we have also some Fourier gravity anomaly, which was investigated many years ago by people in Japan and other places. Okay, so we started the theoretical approach, and we started at that time to work with people in Caltech, with Yann Arms and Jean-Paul Ampuero. And I will show you some development, because there was a lot of debate. It was not so evident to find the right solution. And we also developed and expanded the normal mode theory to this kind of problems. Okay. The change in gravity associated with earthquakes is not completely new. It was measured, the static gravity change was measured about almost 20 years ago after some big events. And for example, with ground-based station, with using superconducting gravimeter, and the signal is slightly larger. You see that now it's about 1 microgal, 10⁻⁸. And it was also observed from satellite Gauss and Grace, and before and after the Tohoku earthquake. But again, it was the static gravity change. What we look for is a transient signal during the earthquake, and it was never observed before. Okay, so we started the search for this signal, and very rapidly we realized that the site of Virgo is too noisy. It is unfortunate, but that's a lesson for the Einstein telescope, that we have to be very careful in terms of the seismic environment. And so what we did was to look for at another place closer to the epicenter. So it is there is a superconducting gravimeter at Kamioka in Japan. It's about 500 kilometers away from the epicenter. And the reason why we work on Kamioka is very easy to understand. It is far and not too far from the epicenter. It's an excellent station because it is installed in a mine at the Kamioka Kande Observatory. I guess people from the gravitational wave community know this observatory. And superconductive gravimeter are so far the best instruments for measure the Earth's gravity field. And an important point is that they had some continuous data. Usually, these kind of instruments only record 1 sample per minute, but in that case, they record 1 sample per second, which was very useful for investigating the whole seismogram. Okay, so these are the data, and it is several days of data. We see the pre-shock 2 days before, magnitude 7, and afterwards you have the big Tohoku earthquake, and you see that you saturate because it is so strong, so that superconducting gravimeter was saturated. And we look in detail to the signal. And of course, one main difficulty is that the source time function here lasted more than 100 seconds. And so what we want to see is the signal before the arrival of P waves. And P waves arrives about 60 seconds after the beginning of the rupture. And during the first 60 seconds, you have about 30% of the moment release. So we really have to look at the first 60 seconds after the start of, I forgot, no, okay. Oh yeah, I forgot one thing, it's okay. We also looked at some other data in a broadband Japanese network. And we have this kind of data, and we had to make some processing. It is very noisy, so we have to make some filtering by applying some window. And we see that the red line here is the beginning of the earthquake. We see that we have something. It's quite small, to be honest, because you see that it is just at the level of noise. And so we have also this Kamioka data, which is slightly better, where we have a better estimate. And we stacked the different data to get this signal. And you see that it looks to be fine, and that we have a signal-to-noise ratio, which is larger. Physicists were, my colleague from physics, were very skeptical because they say, okay, you have to make some statistical analysis. I don't want to reproduce here, but I can give you details if you like. And we show that it is significant at not 5 sigma, like some discoveries, but only 3 sigma, which is not so bad for a geophysicist. Okay, so we have a signal. Okay, but we publish these results, and Tom Heaton from Caltech said, no, it's impossible. The signal cannot be observed because you have a complete compensation with the acceleration of the ground, so it cannot be observed. Okay, so he was partly right, but partly wrong, of course. And what we did, we started to work on the modeling of this signal. Okay, I don't want to detail these basic equations. You know, I guess, most of these equations, which can be integrated to solve them. But what is important in these 3 equations is that we have a full coupling between the gravitational perturbation and the displacement u. And so if we look in detail to the response of a seismometer, clearly, okay, again, we have this second order partial derivative equation, and we have this term which shows that effectively we measure the difference between the ground acceleration and the gravitational perturbation. So we had to understand why we observe a signal, because most of the signals should be cancelled. And by the way, it's a work by basically by Martin Vallée, who did some numerical calculation showing that we have effectively the direct effect. But what is important, the main argument of Tom Heaton was in an infinite medium, but we have a surface, and so we have a boundary condition, and so we excite not only the direct effect, but we have also some propagation of P waves, which will also create some gravity perturbation. And the best proof was provided by data. As usual, we have always to go back to data. And when we did the calculation, we realized that we must not be too close to the earthquake because P waves arrive very rapidly and the rupture did not progress so much. But if you look at these blue lines, we realize that if we are between 500 kilometers and about 1,500 kilometers, we have a maximum of signal because we have 2 competing effects. We have the rupture, which is progressing, which is going on, and we have the decrease with the distance. And so we have this optimal distance, epicentral distance range where we could make some observations. And it is what did Martin Vallée in a systematic way. He looked at many broadband stations in China, Mongolia, Japan, of course, and Korea. And he observed that for good stations, we have this signal, which is clearly visible in many stations. And again, you have to realize that it's a very small signal. You have the scale, 0.1 nanometers, not millimeters, nanometer per. Oh no, the signal is in red. It is 1 nanometer per square second. Whereas when P waves are arriving after the green tick, you have 0.1 millimeter. So you see a very large difference between this small signal and the seismic P waves. Okay, and so when we look more carefully to this signal, we make some numerical modeling, which is quite nice, and we see that we have this signal here. And an important point is that we observe this signal because the earthquake was huge, magnitude 9. And if it should have been downscaled to 8.5, it is the blue line, it could not have been observed. So it's the main limitation. It can be used for very large earthquakes. There are many other observations at that time. And that's maybe some more since 3 years ago. But you see that it was observed for different tectonic environments. And for example, we were surprised to see that for the Wharton Basin earthquake in the Indian Ocean, which is a strike slip, actually the signal is quite strong. So when we think about gravity, we think of vertical component, but we have also horizontal components. And so it is what we see here for the Indian Ocean, where we have this clear signal. But again, all these earthquakes are magnitude larger than 8. Okay, so it can be observed for different kinds of earthquake, strike slip, deep slip, and reverse deep slip. And of course, it was comforting our discovery that there is really a signal, quite small. Okay, so I guess at this step we realized that we really discovered a new kind of signal. And of course, the idea was to apply what we did to earthquake early warning system. So it's an ongoing project. And for people who are not familiar with earthquake warning system, so far it is based on the difference in velocity between P wave and S waves. As you know, P waves propagate faster than S waves. And so when you have a P wave which is detected, a strong P wave, you can make an alert. And of course, if you are not too close to the epicenter, you have some seconds to take some precaution before the arriving of destructive S waves. And of course, you see that it's easy to understand that P waves are propagating at 5 kilometers per second, which is much slower than the speed of light. And that's the reason why, if we can detect the prompt earthquake gravity signal, we will save time. And when we save time, even some seconds, we save lives. And I give this example that when you have an early warning system, you can control trains, you can stop cars, you can prevent traffic accidents, you can stop nuclear plants faster, you can stop plants in general, you can stop many things, and so you can inform the population that big waves will arrive and might be destructive. Okay, so recently we wanted to check the limitation of the technique and how it could be used for practical implementation in earthquake early warning systems. So this work, it's not my work, it's the work by Andrea Licciardi and the group in Nice, and they published a recent paper last year. And what they did was to search for detectability of pegs, which is a prompt elastogravity signal, with broadband seismometers, which are presently existing. And so you see that they define PEGS net, which is composed of many stations in Japan. Where is the center of that? And also some stations in Asia, in South Korea, and so on. So the basic idea is to train the network to recognize the PEGS signal. And so, of course, there are very few observations. So what has been done was to make a training on synthetic data, because we do not have enough real data. And as I told you, the synthetic data are quite reasonable and quite good. And that's an example of what we observed in MDJ, which is in China. And you see that synthetic data and the real data. And of course, to train the system, we add some noise to the data. And we have to consider all possible potential destructive earthquakes in this area, basically in subduction zones along the blue-green lines. And so 500,000 synthetic seismograms, 500,000 synthetic earthquake sources have been considered and calculated. And we use some a priori information, which is a potential location of earthquakes by using SLAP 2.0, and also potential distribution of earthquakes. And for the source time function, we use a classical source time function, which was derived from many studies. And finally, they developed in Nice this kind of a convolutional neural network, which was trained to detect the prompt earthquake gravity signal. Okay, so that's different technical points. So you have this convolutional network, calculate synthetic data, and you define a window where you will make the correlation between the synthetic and data. And finally, you can derive, you can make a decision if there is or not a signal. And so the model is designed to track the evolving magnitude, but so far not to forecast its value. Okay, so that's the results of an example of synthetic test. The blue line is the source time function, and the red line is how you retrieve, when you detect the signal, how you retrieve the evolving moment, so the magnitude of the earthquake. And you see that after 50 seconds, basically when the moment release is larger than 7.5, we start to have a good agreement between the synthetic, between the retrieval of the moment and the source time function. So it was quite successful if can be applied, of course, for big earthquake. And that is the main limitation that I will show you. Oh, I forgot to. Okay, so it is the same figure, but comparison with other techniques. And it's important to realize that during the Tohoku earthquake, GMA, which is Japanese Meteorological Agency, in charge of the warning system, never determined before at least 30 minutes the right magnitude. And that's a real issue because the magnitude determined from P waves was only slightly smaller than 8. And you can easily understand that when you have a magnitude 9, the tsunami was much larger than what was expected from this magnitude 8. So that's the example where with PEGS we can detect after basically 100 seconds the real magnitude of the Japanese earthquake. There are some other techniques. One good competitor is GPS data, which is here in the B4s, where you have this estimate almost as good as the determination from the pegs. Okay, so you can see that the main advantage of this technique is to provide an accurate estimate of the magnitude. Okay, so that's the accuracy and the residuals. And so you have a good accuracy when you're in the yellow area, and you have the accuracy of about 0. You see 0.2 magnitude. But you see that if you consider earthquakes smaller than 8.2 or 8.3, the accuracy is not as good, and that's the limitation. We can see that so far with the classical broadband seismometers, it's almost impossible to detect earthquakes smaller than 8.0, basically. There is one counterexample in Alaska, where there was a US array, and there was a magnitude 7.9. But in that case, the situation, the distribution of stations was very favorable, because you have 100 stations, broadband stations, high quality, and for this Alaska earthquake, it was possible by stacking all the data to detect a magnitude 7.9. But it was very rare to have this kind of distribution. So the idea is that we need a new instrument. And again, we started to work with our friends from the gravitational wave community. And so far, we detect pegs with broadband seismometers. But as I told you, we have this problem of the gravitational acceleration. And because we can only measure the difference between delta G and the acceleration of the ground. I'll say the simple idea to apply is to say, okay, instead of a seismometer, we put two seismometers, and we define the gravity strain meter. In that case, we get rid of the ground acceleration. And so in that case, we work on the gravity gradient, and we can have a better estimate of the gravitational anomaly. And well, okay, the equation. So it's a simple idea, and we try to look at different kinds of instruments, because of course we want to work at long period for seismologies. I mean at periods longer than 10 seconds, because we want to get rid of the microseismic noise. And so that's the reason why we have to work at long period. And so again, when we discuss with people from the gravitational wave community, there are not so many alternatives. You want to have an instrument not too expensive, but very sensitive. And as I told you, there are the superconducting gradiometers, where you put two instruments, and in that case, it's one possibility, but so far they're not really operational. There's some other very promising research about atom interferometers. In that case, you use cold atoms, and you can measure the effect on gravity on the fall of cold atoms. And the third possibility is the torsion bar, which was named TOBA, which was proposed maybe 10 years ago by University of Tokyo. And in that case, you use a rotation induced by the gradient of the gravity field. You have a bar, and when you have a gradient, it tends to rotate, and you have two bars to stabilize the system. But it's a very simple idea. And you have a test mass bar, and we use a tidal force induced, well, the force is induced by the gravitational wave. Well, no, it was, excuse me, it was designed for the gravitational wave, but in our case, of course, we don't want to detect gravitational wave, we want to detect gravity anomaly. Okay, excuse me. And so these ideas came up with a proposal named the Pegasus detector for prompt earthquake gravity anomalies early warning system, and based on torsion bar. Okay, so as I told you, initially it was supposed to work to detect gravitational waves at long periods, so at periods longer than 10 seconds. But actually, for gravitational waves, it turns out that it's not so efficient because, of course, when they did some experiments, the sensitivity was only 10⁻⁸. And if we want to detect magnitude 7 earthquake, we have to go down to 10⁻15 by square root of Earth. Okay, and so these are some mock-ups of this TOBA, and we started to work on how to develop a TOBA instrument, torsion bar instruments, for our application in seismology. Okay, and so of course you easily realize that there is a huge gap between 10⁻⁸, 10⁻15, and it was a real technical challenge. But people working on gravitational wave, on Michelson interferometers, VIGO, LIGO, it is the same issue. They did much progress from 10⁻⁻10 to 10⁻24. So it means that they were quite confident that it is possible, difficult but possible. As I told you, they use this nice inverted pendulum for stabilizing the system. Okay. Okay, so the readout system is also based on the Fabry-Perot cavities, interferometers, and it's quite sophisticated. It was designed by people in APC in Paris, astroparticles laboratory. What is very important is the isolation system, which is, okay, again, I don't want to detail the different points. What is important, of course, is again the suspensum steering stage and the inverted pendulum to make very stable bars in the center, and of course everything is a vacuum and must be very well isolated. We also complement this. Okay, so again, it's complicated image where we really try to investigate the different sources of noise. Okay, I didn't want to show it, but anyway, if you want to discuss the different sources of noise, we can do it later on. It was complemented by a seismic experiment, and several times we have shown that in south of France, here in a very nice environment, there is an underground laboratory, and the main advantage of this laboratory is that it is a three-dimensional, because it was supposed to be used during the Cold War to and there are some nuclear missiles which were installed in this plateau, and now it is only devoted to scientific experiments. And so it's possible in this laboratory to have very deep instruments, about 500 meters below the surface, and to have as well some surface instruments. And that's, as Katharina mentioned, one of the main issues is the Newtonian noise. And it's very difficult to have a good estimate and to get rid of the Newtonian noise. So we decided in this project to have a specific experiment where we will install different kinds of instruments to try to get rid of Newtonian noise. So they will have broadband seismic networks, microbarometers, eventually rotational sensors, tiltmeters, and so on. Okay, so it was the plan. So far, it is not yet accepted, so I don't know what will happen. And that was a fact. Oh, what's going on? Oh. What's going on? It's almost, it should be okay. Yes. So that is a final plan where we wanted to develop about 3 instruments in different places. One in Rustrel, but other ones in more active zones from the seismic point of view. So we should have these Pegasus instruments, which will be connected to an earthquake alert center. Everything will be complemented by seismometers, of course, and these instruments should be able to send a warning to the population. So that is where we are now. So far we wait for money. And what I try to show you is that we start from very simple ideas, gravity field measurements, and we end up, which was completely unexpected, with earthquake early warning systems. And what happens is that by chance, I should say, we detect a prompt gravity signal. This signal is quite small, so it was observed for the Japan Tohoku earthquake, and so it was huge earthquake, so very favorable conditions. It was detected at Kamioka, which is in a superconducting gravimeter, but as well in very broadband stations in Japan and Eastern Asia. And now we would like to implement this kind of detection for earthquake early warning system. And as I told you, the main interest is the very rapid estimate of the magnitude, which is impossible with classical techniques. Okay, but as I told you, if we want to detect smaller earthquake, we need new gravity instruments, and we have several possibilities, and our favorite choice is the torsion bars, TOBA, but we still wait for funding. Okay, so I tried to show you how we start from basic ideas and we end up with what we consider some kind of new field, the speed of light seismology. Okay, thank you for your attention.